All right, welcome to part 2 of chapter 7 for Intro to CIS for Messiah College. Last time we covered some introductory concepts for problem solving and algorithms. So just to recap, we talked about the benefits of problem solving, different steps of Polya's problem solving process, how to use pseudocode and the benefits that it provides, as well as examples of different algorithms. Now today we're going to be talking about specific examples of algorithms that have been developed by the computer science community to address specific problems, and they're going to be really helpful for you in the future in terms of just learning what kinds of methods can be used to solve these common problems. So first we're going to talk about different searching algorithms. These will allow you to find values in collections. We're going to be talking about, we're going to be talking about arrays, but searching and finding data in a collection is a very broad topic, and there are many different research areas that deal with, depending on the kind of data collection, the way that it's set up, the structure, is if it's in a tree or if it's in a heap or if it's in a database, what kind of steps would you take to find an item of interest in that collection. And this is what a search engine does for you. This is what Google does behind the scenes. There are very diverse and exceedingly complex different kinds of searching algorithms. We are going to be limiting ourselves to just a couple simple ones. And the first one is what I think of as one of the most straightforward, one of the easiest kinds of searches to go through, and that is a sequential search. And a sequential search is exactly what it sounds like. You step through your collection, in our case an array, looking at each item in order to locate the value that you're interested in. So if you are studying for, let's say, a Spanish vocab quiz, and you have a stack of index cards, and each index card has a different vocab word, and you're learning these vocab words, and you're trying to find one specific word in the stack, chances are you will probably just go through each card in the stack in order until you find the words you're looking for. This algorithm is really beneficial to us, A, for its simplicity. It's, a very common method that we use in our everyday lives. But it's also useful because your collection, your array, does not have to be sorted in order to utilize this algorithm. You simply step through each element in the collection until you find what you're looking for. So for a pseudocode example of this algorithm, let's say that we have an array of numbers that we just call numbers, and we have a value that we're looking for called search item. Then in order to find search item within our array of numbers, this might be a little snippet that we would utilize to accomplish our goals. So let's say we have two local variables. We'll call them position and found. And position can be used to track the current spot where we are in the array, for comparison purposes, and found is what it sounds like. It is simply a flag, true or false, indicating that we have found the value that we're looking for. So starting with position equals 0, we end up with a compound condition to govern the execution of our loop. So while position is less than 10, so if we are assuming that there are 10 elements in our array, and found is false. So in order for our loop to continue, both of these conditions must be true. They both must hold. So this gives us two ways out of our loop. Either we get to the last element in the array, and there is no There is no value available for us, in which case it does not exist in the array, and that is just the end of the loop, which is a valid result. It does not necessarily need to be in the array. Or we find the value that we're looking for. So either position is greater than or equal to 10, which means we got to the end of the array and did not find the value we're looking for, or found is true, in which case we did find the value that we're looking for. And both conditions will end the array, or will end the loop, I'm sorry. So once we're inside the loop, we need to do our actual comparison. Is the value at our current position in the array equal to the value that we're looking for? If so, set found to true, and this means that the next time that the loop goes to iterate, that condition will fail. So found is false becomes found is true, and now the loop ends. Or if the current position does not equal the value that we're looking for, increment the position variable. So now instead of 0, now it's 1. And look at the next value. So the next time that we go through the array, position will now be equal to 1, and we can look at the next value, and so on and so on. So as I said, this is a very common kind of algorithm. I'm sure that you've used this in real life, but it is fairly inefficient, because in order to satisfy one condition or the other, or to violate one condition or the other, you either need to find the value that you're looking for, or you need to step through the entire array. That is a vast number of comparisons, especially if your array or your collection or whatever you're using is of large size. So how do we improve on this simple but inefficient algorithm? Well, one example would be to sort your collection, to sort your array. And in this particular case, if you get to a point where the value that you are observing at the current location in the array is greater than the value that you're looking for, you can assume that everything after that point will also be greater, and you can just end your execution. If you haven't found it up to this point, no value that you encounter later is going to work either, so you can just short circuit that logic and exit the loop and return a value if not found. So in this particular example, we have two new items here in red. These indicate more complex chunks of logic that we're going to talk about in a minute. So if we have one chunk that is responsible for reading in an array of values, let's say, and we would then display to the user, enter a value you want to search for. Great, we read in the value from the user, and we have another separate chunk that looks for that search item and sets the flag for found to true or false. Excuse me. And then depending on the result, we display to the user item found or item not found. So for these more complex chunks, reading in the array and then actually searching the array, what might those look like? So reading in the array, we have some logic here that gives us a collection of whatever size the user wants. So in this way, if I want a collection of 10 elements, but Bob wants a collection of 50, we can both use the same code. So we request the number of values that the user wants to utilize. We read that value in, and then stepping through from 0 to that number of values, because remember, arrays are, the index of an array starts at 0. So then we can set the value at that index for that data point according to whatever the user provides. Now, this isn't necessarily integral or very important to our search example, but it does give you a little insight into good software engineering practices. you don't want to just assume that everybody's going to use the same parameters. You don't want to assume that everybody's going to run through things the same way. So writing dynamic pieces of code like this allow you to apply and reuse and extend the utility of your code to many, many different situations. So this here is more of an example. I included it because it's useful for general software engineering practice. So keep this one in mind. Now, the meat of the algorithm, actually searching for the item we're interested in. Now, this should look very familiar compared to what we were looking at before, but we have a new comparison statement inside the loop. Remember, index being the position that we're currently at, length being the value, the number of values that the user provided, and our found flag, which is the same as before. But now, not only are we looking for is the value that I'm currently comparing equal to the search item, but is it also greater than the search item? Because if so, then it's not going to be available in the array at all. It's just not going to be there. So we can set our index to length, which short circuits the first condition of the loop and ends the execution of our algorithm. Again, we are making an assumption here that the user is giving values to us already in sorted order. If the user does not give us those values in sorted order, then this sorted sequential search example is not going to work for us. So we are putting a lot of pressure on the user to make this work for us. But again, we will be discussing even more mature and flexible algorithms in just a minute. Now, what does the sequential search actually look like? Well, I have this handy little animation for you. The peach or orange or whatever color bar that is, about 3/4 of the way through the sequence there, that is the value that we are searching for. And the red bar is the current value that we are evaluating or comparing against. And as you can see, you simply move through the collection until you get to the value of interest. So in this particular example, obviously our array is not sorted. So if the peach colored bar was not present in the array, we would have to go through the whole thing in order to be able to confidently tell the user, sorry, your value was not found. Now, a little different format here. What if we were interested in the value 6 in this shorter array with values 3, 2, 1, 6, 4, 5? So if we're interested in value 6, so then we would start with the value of 3 at index 0, and as we would assume, the value here needs to be compared against the value that we are interested in, so 3 and 6. 3 does not equal 6, obviously, so our condition, our match condition, is not satisfied, so we need to go to the next value. So moving over to the next value, in this case this would be index 1, the value at index 1 needs to be compared to whatever expected value we're searching for. So in this case, the value at index 1 is 2. 2 does not equal 6, and therefore the match condition is not satisfied, and we move on to the next element. So in this comparison, we are now at index 2, 0, 1, 2. The value here is 1. 1 does not equal 6, so again, the match is not found. Go to the next item. The value that we're looking for is at index 3, 0, 1, 2, 3. And lucky for us, 6 does equal 6, so the search is found, or the match is found, and search is complete. So this is a little more a hands-on kind of comparison here, and you should be able now to answer question 1 in the partner activity. So it might be a good idea if you wanted to pause the video now and go to the partner activity and work on question 1, and then you can come back to the video whenever you're done. Okay, so if you've taken time now to complete question 1 in your activity, we can move on to the next search algorithm. This algorithm, a little more involved than the sequential search. This is what is known as a binary search. So this specific algorithm breaks up your array in half multiple times in order to locate your value. The primary difference here is that binary always assumes that your array is sorted. If it's not sorted, you cannot apply the binary search algorithm. And I'm hoping that we will demonstrate to you exactly why that is the case. So in general terms here, so again, we're dealing with an array of numbers, and in this particular situation, we called the array data, and the value that we're looking for is search item. So we have 3 local variables that help us to accomplish the search logic that we're looking for. So we have first, which is the beginning index of the chunk of the array that we're going to look at. Last is the last, obviously, index of the chunk that we're going to be looking at. And the first, the initial values that we're going to use for first and last are 0 and length minus 1. So remember, with your array indices, your first array index is 0 and your last is n, or the number of elements, minus 1. So if you have an array of 10 items, then the index of first item would be 0 and the index of the last would be 9. So by setting first and last to these values, we guarantee that the first time through the loop, we will evaluate the entire array, the entire collection of values. We also default the found flag to false because, of course, we need to actually find it. So the first step in the search is to locate the middle of the current collection. So if we're starting with 0 and length minus 1, then the middle will be obviously the middle of those 2 values, and we calculate that as first plus last divided by 2. So if you have an array of, we'll say 9 elements, for example, then your length is 9 minus, or your length is 9, so last index is 8. So first is 0, last is 8. 8 divided by 2 is 4. And that, because there are an odd number of elements, middle is set to an actual index number. If you have an odd or an even number of elements, so 10, in which case your last index would be 9. 9 divided by 2 is 4.5, but there is no index 4.5, so we simply use the integer part of that value, which is also 4. So in that situation, we compare the value in the in index number 4, so data at index middle, which is 4, and if that's the value that we're looking for, fantastic, set the flag, the found value, to true. Otherwise, we need to reset the values of first and last and go through the loop again. Now, this is the interesting part of this algorithm, because this dynamic kind of relationship hones in on the value that we're looking for much more effectively than simply stepping through each value in the array. So we look at the current data value and compare it to the search item. Now remember, we're assuming that the data collection is sorted. So if the search item that we're looking for, the value that we're looking for, is less than the current value that we are observing, data middle, then we can make the assumption that the value that we're looking for is going to be in the left part of the data collection. So it has to be less than, it has to be earlier in the array than where we currently are. If the search item is greater than where we currently are, then it has to be in the latter half of the array. It has to be down the line. So in that case, we have to shift the bounds of the array, the bounds of what we're looking at, the bounds of this current chunk, according to where we think the search item is going to be. So if the search item is going to be in the first half of the array, then we set last to middle -1. And what this does is it chunks up the array, and now we are only looking at the left half. We are only looking at 0 to 3. If the middle is 4, then we are only looking at 0 to 3. If the value is greater, now we set first to middle +1, and we leave last alone. So first would now become 5, and last stays as 8 or 9, depending on which one you're using. So last stays the same, and first is updated. So now going through the loop again, now we're either looking at the first half of the array if the value is smaller, or the second half of the array if the value is greater. And going on and on through the iterations of the loop, we start to really decrease the search area of the array by going left or right and looking at subsequent halves of whatever current chunk we're looking at. I know this can be a little difficult to wrap your head around, so I have another little animation for you. In this situation, green is the block that we're looking for, and red is the middle of the current chunk. So you can see that the red bar starts at the middle of the overall array, and then it moves to about 3/4 of the array, and subsequently shifts back and forth, moving through smaller and smaller pieces of the overall array until it gets to the value that we're looking for. Again, this could be a little abstract, so I have another little table here for you. So let's say that we have, instead of just numbers, let's say we have a sorted array of words, and we have this list of animals, and we're searching for the value of cat. So if we're searching for cat, then we start with the first value being 0, which is the first index, and last being 10, which is the last index. So for that particular calculation, we end up with a middle value of 5, which is, or a middle index of 5 and a value of dog. Now, alphabetically, cat comes before dog, so we cannot return a result yet. We're still searching. So now first remains the same, and because cat comes before dog, we change the value of last to middle -1. So last is now 4. So our search area now gets shifted from the entire array to only from ant to deer. And the middle value for 0 to 4 is 2. Sorry, the middle index is 2 with a value of chicken. So when we compare cat versus chicken, we have, again, a cat is alphabetically smaller than chicken. So we evaluate our first and last indices again. Cat comes before chicken, so first remains the same, and last now becomes 2 minus 1, which is 1. In this situation, again, the normal value would be 0.5 or 1/2 if we wanted to evaluate for a middle index, but there is no 1/2 index, so we just use the integer part of 1/2, which is 0. So now we're comparing cat versus ant. Cat is alphabetically larger than ant, so we now update the first index and leave the last index alone. So first, 0 plus 1 is 1. So between first and last, they're the same value, so the middle index is also 1. Cat equals cat, so the value is found, and we return true. I'm hoping that this sort of breakdown helps you kind of grasp this idea a little better. Now, what happens if we're searching for a value that doesn't exist in the binary search tree? So let's say we're searching for zebra. So again, we start at first is 0 and last is 10, middle is 5. So comparing zebra against dog, zebra is greater. So we update the value of the first index and leave last alone. So middle, 5 plus 1 is 6. So between 6 and 10, the middle index is 8. Zebra is greater than horse. So we update the value of first again. 8 plus 1 is 9. Between 9 and 10, obviously the middle index would be 9.5, but there is no 9.5, so we simply take 9. Zebra is greater than rat, so we increase the value of first again. 9 plus 1 is 10. 10 and 10 are the same value, so the middle is also 10. Zebra is greater than snake, so we update the first value again. Unfortunately now, first is greater than last. You cannot have an 11th index in our array. So the first condition of our loop is compromised. First cannot be greater than last, so we return a value of false. There is no value zebra in our array. So hopefully this makes it a little easier for you to wrap your head around. So I'm going to give you a moment. This should be a good point for you to pause the video and work with your partner on question 2. Okay, so coming back from the partner activity, we are now going to talk about different sorting algorithms. Up until this point, we have been concerned with the